Well, Year 12 is your first lesson this week. Moving on from the differentiation we've been doing, we're going to be looking today at probability distributions. So you've already looked at some probability this year in terms of just understanding generally kind of how probability works and how different things can be kind of calculated, just slightly really extending the work that you'd already done at GCSE on probability. And we're going to be taking this forward now into some kind of new areas. Everything that we do in today's lesson, though, isn't necessarily new. It's just a new kind of notation in some places, and then just some kind of terminology that we need to be aware of, and so just some different types of problems that we need to be aware of kind of moving forwards. So what is a probability distribution? So when we have an event that has several different outcomes, we can define what we call a random variable that describes the number of times or the different outcome it is that happens from that event. So, for example, in this table here, which is one of the forms you'll see representing probability distribution, we're talking about a discrete random variable x, which represents a score shown on a fair six-sided dice when it's rolled. So in terms of this, what we can see in terms of this table is fairly easy to understand in terms of the general what it's trying to convey to us, that x across the top is our variable, is the score that you can get on that dice, so 1 to 6, and then underneath you've got the probability of actually having that score, which is a 6 for every single value because it's a fair six-sided dice. Now, what we're talking about then with the probability distribution is any way that we can use to describe the probability of any outcome in what we refer to as our sample space. Now, sample space is a term that we've come across before in terms of things like sample space diagrams, where you use a diagram, usually a two-way table, to list all the different outcomes of an event. So what we're talking about here is probability distribution describing the probability of getting any outcome possible in the event that we're discussing. So this table is a probability distribution. It's just simply describing probability of all the different possible outcomes. But as we're going to see in a minute going forwards, there are some different ways that we can describe these probability distributions, different ways we can write them down and go from there. Now, just going back a little bit, we talk about this discrete random variable x. So it's a variable because the number on the dice varies, it can change, you can get different numbers. But the discrete and random part, well, random because it is completely random, it's not affected by human interaction or anything like that. And then discrete is a word that we use in statistics when we describe that there are only certain values that can be taken. So it's not a continuous variable, and that's something we're going to have to be able to kind of differentiate between moving forwards, particularly into year 13. So a discrete variable is all we're going to be focusing on in year 12 with this kind of work. So there are certain values it can take. You can't get a 1.5 on a dice or a 2.09 or anything like that. There are certain numbers dictated that you can get. Okay, so you're going to see lots of questions like this where we've got this table kind of set out, the same kind of notation where you've got x, which is the variable, which will be defined in the question. It will be described as what x represents. Then underneath, you notice I've got p, and then in brackets, x, so capital X equals lowercase x. So that bit of notation is saying here that the capital X represents the variable and lowercase x is used to represent the specific value that we're discussing at that moment in time. So where x is 1, this is probability that x is 1, where x is 2, probability that x is 2, and so on and so forth. Okay, so it's just a little bit of notation you've just got to kind of be aware of there. So in terms of this, it's just describing, like I say, probability you get all different numbers of dice. Now, you can be asked lots of different questions from these kind of tables moving forward. So, for example, we could be asked what probability that x equals 3 is. Then we simply look up that value in our table as getting 1/6. We could be asked what probability that x is greater than 4 is. Now then we'd have to think a little bit and say, well, the outcomes that are greater than 4 are 5 and 6. Probability of those are both 1/6. So if it's either going to be a 5 or a 6, from standard rules of probability that we've talked about before, You would then add the probabilities together, so 6 out of 6, 2 6, or 1/3 when you simplify it. They're just straightforward kind of questions looking at these kind of ideas. So if we look at some other simple examples moving further on, okay, so we want to talk about then flipping a coin. So another classic kind of example in terms of probability. So if you've got a fair coin flipped 3 times, we might want to list all the potential outcomes. So I've gone through in that list there and written down all the potential outcomes you can get from flipping a coin, where H stands for getting heads and T stands for getting the tails. There are 8 of them. Is that probability distribution yet? No, it's not, because as I said before, it's got to be able to fully describe the probability of any outcome in the sample. Although it implies the probabilities, if we think about it, it doesn't fully describe it. So that's not a probability distribution yet. It's literally just a list. It's actually the sample space, if you like, because it's talking about all the range of values that you've got there listed there. But it doesn't dictate the probabilities, like I say. So moving on from that, if we now say though that x is the number of heads, so again we've got a random variable x, a discrete random variable x is the number of heads we can again set out a table for this. So if we're flipping 3 coins, we'd have to think to ourselves, well, how many heads can we get? Well, we could get no heads in the instance that they're all tails, 1 head, 2 heads, or 3 heads on their instance where they're all heads. So in terms of my table, it would look something like this, where you've got x then now again being the number of heads, so slightly different to the first example with the dice where x represented the value shown on the dice. Here we've got the number of something, so more of a frequency kind of idea going on. And then underneath again, probability that x equals x, the probability that x equals 0, i.e. there are 0 heads, would be 1 out of 8. How do I know that? Well, looking at that list, thinking about it, there are 8 different ways, 8 different possible outcomes, I should say, when you flip these 3 coins, and only one of them is tails, 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 so giving you probability that x equals 0 of 1/8. For getting 1 head, we go through the list, you'll notice there are 3 ways of doing that, so it'd be 3/8. For 2 heads, again 3 ways, so 3/8 again, and then for 3 heads, there's only one way of doing that, head, heads, heads, so you get 1/8 for that. So that then is a probability distribution describing this example, okay? However, there are then other ways that we can describe probability distributions, like I say, which are a bit new and a bit different. So it's just a case of just learning about them and just being aware of how they work. So this is another way of describing that same probability distribution. So this is referred to as a probability mass function, okay? So in terms of this, what we've got here is the probability x equals x notation used on the left, and then this kind of curly bracket going out, showing all the different probabilities that exist. So not all the different outcomes listed first, but all the different probabilities listed going down the page. And then next to them, you've got the values of x, which would give that specific probability. Okay, so where we've got the 1/8, to the right of that, we've written x equals 0 or 3 to show that the probability of getting 0 heads or 3 heads are both 1/8. For the 3/8, you've got x equals 1 and 2, showing that the probability of getting 1 head or 2 heads would both be 3/8. Now down the bottom, then you've got 0 and the word otherwise next to there. Now that's always kind of included just for completeness, for showing that because this is a discrete function, the values that we can get in this function for the variable are 0, 1, 2, and 3. The number of heads we can get, because we only flip 3 coins, are 0, 1, 2, or 3. Other values of x, theoretically, mathematically, they can't happen here. So hence the probability is 0. So that's what that 0 otherwise represents there. And you'll always get that at the bottom of your probability mass function. So one thing to be aware of with all of these functions that we've talked about a lot before, going back, a long time into our work on probability, GCSE and before even, is that we've got to be aware that there are simple kind of rules that apply to all of these kind of probability questions. And one of the simplest is detailed here, which is that the sum of all of these probabilities has to be 1. So whenever we've got mutually exclusive exhaustive probabilities, so what I mean by that is that those things can't happen at the same time, so there's no kind of overlap. You can't get no heads and get one head at the same time. In this example, you can't get a 3 on a dice and a 6 on a dice at the same time. These kind of ideas, all the probabilities have to add up to 1. So you can see in our table pretty clearly that those add up to 1. In the probability mass function, it's not as clear because obviously if you just added up 1/8 add 3/8, so you'd get half, you wouldn't get 1. But you would actually add 1/8, 1/8, 3/8, and 3/8, as we've discussed in the table, and as is in kind of shown with that mass function by the fact that there's 2 values that give you probability of 1/8 and 2 values that give you probability of 3/8. So it's just a kind of simple thing that we've just got to remember as we kind of move on and have a look at what's going on further down. Now, those are really simple examples. We're going to look at something that's a bit more like the kind of questions that you're going to face in terms of this lesson, and obviously in terms of like tests and things moving forwards now. So, if you've got then a biased four-sided dice rolled, okay, now we're given probability distribution here as a rule, as an algebraic rule, and this happens quite a lot in these questions, where it's saying the probability that x equals a specific value of x would be equal to k over x, where k is some constant that we need to find. And the first thing you'd be asked to do in these questions, the first thing you'd have to do before you can do anything else, would be to find the value of k. So in terms of then starting with this, I would start off with, if it wasn't already given to me, the table. So on the left there, we've got the table. It in terms of our question, describes this four-sided dice, so it'd have the values 1, 2, 3, 4 on it. So x, the variable that we're using here, the possible values are 1, 2, 3, and 4. And then the probabilities, if we use those specific values of x, where if x is equal to 1, would be k over 1, which is just k. If x is equal to 2, we'd get k over 2. If x equals 3, k over 3. And where x equals 4, we've got k over 4. Now, using that simple fact that we've talked about a lot before, and just reminded you of, that these probabilities have to add up to 1 then, next to that table then I've written that k plus k over 2 plus k over 3 plus k over 4 has to equal 1, by definition probability. Now then, that is an equation that I can solve relatively simply by simply then multiplying actually by 12 here. So I multiplied by 12 because 12 is the lowest common multiple of 2, 3, and 4, so that'll get rid of all those denominators straight away. So you get 12k plus 6k plus 4k plus 3k equals 12 when you multiply every single term by 12. Add up the number of k's on the left hand side, that means we've got 25k equals 12. So then k is 12 over 25. Now, having then worked that out underneath my table, as you can see then, I've then substituted that value for k 12 over 25 into k over 2, k over 3, and k over 4 to write down my fractions. You might be asked to do that separately in a question to actually go through and write down the probability distribution properly with the precise values you've worked out. I've just added it in underneath my table there just to save myself some space. So k was 12 over 25, so k over 2 would be 6 over 25, k over 3 would be 4 over 25, and k over 4 would be 3 over 25. Now then you've got then supplementary questions similar to the questions that we've been asked before. So bottom of my page here, I've got a few more questions to have a look at. So what's the probability that x is greater than 2? Well, the probability that x is greater than 2 is going to be found by doing 4 over 25 and 3 over 25, because the values in this probability distribution which are greater than 2 are 3 and 4. So probabilities of it being a 3 is 4 over 25, probability of it being a 4 is 3 over 25, and if it's one or the other to give us an answer which is over 2, then you've got to add. Underneath it, slightly more interestingly, just thinking about kind of different questions we ask. So we've been asked what the probability of x being greater than 1 but less than 4 is. Well, in terms of that, again, we've just got to think about, well, what values are there in this distribution which satisfy that condition? Well, it would be 2 and 3. Because notice it's not greater than or equal to or less than or equal to, it is greater than and less than. So it excludes the 1 and the 4, and we just focus on the 2 and the 3. So again, we get those probabilities and add them together. Dead straightforward, 10 over 25. We could simplify it. I didn't bother writing it down, but obviously if we simplified it, we'd get 2/5 there. Now, finally, we could be asked questions like, what's the probability that x is greater than 4? Now, this would just be like a 1-mark question on a test just to show that you really understand this. What's the probability that x is greater than 4? Well, 0. Because in terms of this being a probability distribution where we've got all the different outcomes listed as they have to with their probabilities associated with them, then there cannot be a value of x which is greater than 4. It is impossible, therefore that probability is equal to 0. So these are relatively simple questions that you should get used to. The things that can kind of catch people out alongside these are things like using the inequalities along with these questions, and we'll talk more about those as we go through the series of lessons on this topic. But just take your time and think your way through and just think, well, what specific values are included for this different kind of question, this condition that we're imparting on this question. Now, as usual, I'll just very quickly then show you the page and the exercise from the textbook. So here we are on exercise 6A on page 86 in the Mechanics and Statistics textbook. Okay, so we're going to detail for you which questions to go through on these pages. You can see there's lots of E's and P's, the ones we usually focus on going through, and I believe, just double check, yeah, there's a few more questions even over on the next page as well. Okay, so that kind of shows you how common these questions are, because we've got various different examples from exam questions there. So, it shows you how important it is that we focus on this and get this kind of down right before we do any tests or anything like that. So, next lesson we'll go on to look at a specific probability distribution that you need to know a lot about in detail, and how we can apply that and use that for various kind of problems. But until then, goodbye.